Yeah, should we start?
I think so.
Okay. So welcome back, everybody, to one of the invited talks at the APPROX 2020 conference. It's a real pleasure to have Nathan Klein from the University of Washington, who will tell us about his remarkable recent new work on beating the three halves for TSP. The work is, as you guys know, with Anna Carlin and Sharon Obeskaran. So Nathan, all yours.
Okay. Just make sure sharing works. Can you see? Okay. Great. So yeah, hi everyone. I'm Nathan. I'm going to be talking about a slightly improved approximation algorithm for metric TSP. And this is joint with Anna Carlin and Sharon Obeskaran. And before I start the talk, I want to say, please ask questions if you have them. I'd love for people to interrupt me when something's not clear. Okay, so in TSP, you're given as input a list of cities and their pairwise symmetric distances, which form a metric. And the goal is to find the minimum cost tour which visits every city at least once. So if I live in Essen and I want to visit all the marked cities and then return, then TSP will give me the shortest route which does so. The story of approximating this problem began in the 70s when Christofides and Serdyukov independently found three-halves approximation algorithms. And since then, there's been a lot of amazing progress on approximating TSP, for example, in special cases such as planar TSP, where we have a PTAS, and graphic TSP, where we have a 1.4 approximation. However, the general case has remained at 1.5. So in this talk, I'll discuss a tiny dent we made. We improved upon Christofides' algorithm by some epsilon around 10 to the negative 36. And before describing the algorithm, I want to give just two pieces of background. The first piece is pretty standard. It's this linear programming relaxation for the problem. It asks for essentially a fractional Hamiltonian cycle. Every vertex should have degree 2, and every cut should have fraction at least 2. And both of these are true of an integral Hamiltonian cycle, so it's a valid relaxation. And this is known as the subtour elimination LP or the Held-Karp relaxation. And note that it can be solved in polynomial time via a separation oracle. It's easy to find a minimum cut in the support graph and return it as a violated constraint if it's below 2. And as is often the case, it's convenient to think of XE as the probability and edges in the tour. Okay, so the second piece of background, a spanning tree distribution is lambda uniform if every edge has weight lambda e, and the probability of a spanning tree is proportional to the product of the lambda e's in its edge set. So for example, the graph on the left with lambdas 1, half, 1, and 1 would yield the following distribution, with the last tree being the most likely since it has the largest lambdas. And it was proved in 2010 by Sadpour et al. That for any point x in the spanning tree polytope, we can find a lambda uniform spanning tree distribution that actually matches the marginals of x. And they showed we can do so in polynomial time by solving a max entropy convex program. So sometimes I'll refer to these as max entropy trees, since they're from the distribution that maximizes entropy subject to the constraint of preserving the marginals. And as it suggests, these programs always actually produce lambda uniform tree distributions. So in some sense, these are the same notion, max entropy and lambda uniform. And here we'll study an algorithm which is based on a work by my co-author Cheyenne as well as Sabarian Singh. And it's also very similar to Christofides' algorithm, except we choose our tree differently and we actually choose a tree plus an edge. So first we compute an LP solution, x, to the Held-Karp relaxation. And we do so such that there's an edge E0 with cost 0 that has x of E0 equal to 1. And one can actually assume this edge exists without loss of generality. So given this x, we'll compute a marginal preserving lambda uniform spanning tree distribution mu on the support graph of x without this special edge E0. And it's not so hard to see that x minus E0 is actually a point in the spanning tree polytope. So this is a valid step. And for some intuition on why this is the case, note that the sum of fractional value in the TSP polytope is n, while on the spanning tree polytope it's n minus 1. So we're essentially just correcting this discrepancy by removing an edge of fraction 1. And this step is actually the sole difference between our algorithm and Avescaron, Saberi, and Singh's. They instead rescaled the LP by 1 minus 1 over n to place it in the polytope. And we don't expect this algorithm to behave all that differently from theirs, but it turns out to be easier to analyze since here we respect the marginals exactly. So now we choose a spanning tree T from this lambda uniform distribution, and we add back E0, marked in yellow. So we obtain a tree plus an edge. And due to this marginal preserving property, the expected cost of this tree is equal to the cost of the LP, which is at most opt. And finally, we add the minimum cost matching M on the odd degree vertices of the tree union E0. So here the green, orange, and the red edges together make an Eulerian tour, and thus a valid TSP solution. So our goal is now to use properties of our tree to show that the cost of the matching is less than half of opt in expectation. And since the tree costs at most opt, this would show that this is a randomized 1.5 minus epsilon approximation for TSP. Okay. So the rest of the talk is just about analyzing the cost of this matching in expectation. And first I'll introduce the matching LP, which we'll use to model the cost of the matching. Okay, so as I said, we want to find the minimum cost matching on the odd degree vertices of the tree that we sample. And from now on, when I say T, I actually mean T union E0. But for the rest of the talk, I'll pretty much forget that E0 exists. So yeah, it doesn't change anything fundamentally starting from this point. We just sort of use it to make sure we can respect the marginals without scaling. So forget about E0. So now to bound the cost of the minimum cost matching, we'll use this matching LP. Basically, instead of computing the expected cost of an integral matching, as this is a hard thing to get a handle on, we want to instead show an upper bound on the expected cost of a fractional matching between the odd vertices of the tree. So here's the LP, and an example tree we want to augment with a matching where the odd degree vertices are marked in red. So clearly you want to minimize the cost and your variables are non-negative. So let's make sense of this second constraint. Basically, if you select a set whose cut has an odd number of edges in the tree, by degree sum arguments, the number of odd vertices in this cut must be odd. So one of them must be matched outside the set, letting us add this constraint. This set, on the other hand, has no such constraint because these two vertices could be matched to one another. So this is the same as looking at the set, looking at sets with an odd number of odd vertices in the tree. The written constraint is just a more convenient convention. And this LP has a very nice property. It has an integrality gap of 1. So if we can construct a fractional matching of cost C, there must be an integral matching of cost at most C that in fact our minimum cost matching procedure will find. So we're just showing the existence of a cheap solution. And now our approach will be to find a random solution to this LP as a function of the sampled tree, such that all constraints are met, meaning whenever delta of S intersect T is odd, Y of delta of S is at least 1, and to show that the expected cost of the matching of this solution is less than half of opt. And it's actually very easy to get a matching of cost at most opt over 2. If we set YE is equal to XE over 2 everywhere, this is already feasible, since every cut has at least fraction 2 in the TSP LP, and thus in this solution, every cut has at least fraction 1. So we simply satisfy constraint 2 in the matching LP for every cut, not just for the odd ones. And this costs half of the LP, and so we immediately recover the 3/2 approximation of Christofides. However, as I said, this assignment simply makes every cut at least 1, so we're satisfying constraints that might not actually exist. So the hope is that maybe if a lot of cuts have an even intersection with the tree, and hence a lot of these constraints just go away, then perhaps we can set ye to be strictly less than xe/2 in expectation. For example, if some edges magically happen to be in no odd cuts, we can set their ye value to be 0, as there are no constraints. So if we can do this, then we gain some epsilon with respect to the initial feasible solution, and we obtain a 3/2 minus epsilon approximation. And just to be clear, what I mean when I say even and odd, I'm going to use this as a shorthand for cuts. I'll say a cut is even if its edges have even intersection with the tree, and otherwise I'll say it's odd. Okay, any questions up to this point? Okay. So we can think actually of this xe/2 solution as our initial point. And now we'll perturb it a little bit by applying a slack vector that depends on the tree, such that we set ye is equal to xe/2 plus this slack. And this slack may be positive or negative. So think of us as starting at a feasible point and then taking a small step in a direction which in expectation makes every SE negative. In other words, sending the expected value of every ye down. And as long as SE keeps y feasible, this implies our goal. So now we want to construct such a slack vector such that it's always feasible. In order to help us maintain feasibility, our third criteria is that our slack vector will be very, let's say, subtle. We'll move variables by a tiny fraction eta at most, guaranteeing that each slack is at least negative eta/4 times xe with probability 1. And I say large cuts here because this lets us forget about all constraints in the matching LP that correspond to large cuts in X. So in fact, the only constraints we're now concerned about, given this feasibility requirement, have delta of S less than or equal to 2 plus 2 eta. So take any cut that's larger, and even if we set all slacks in that cut to their minimal value, the constraint is still satisfied, even if it's odd. So for the rest of the talk, we'll only be concerned with the small cuts, which I'll call the near minimum cuts. And I say near minimum because our LP ensures every cut is at least 2. So basically, we're looking at constraints that are very, very close to being tight. Eta will be very small. You may actually wish to think of it as being 0. And since we generate negative slack from these missing constraints in the matching LP, it's very crucial that many of these constraints corresponding to near minimum cuts are actually missing. If they weren't missing, we couldn't do anything. So this approach only works for distributions that in expectation have many even near minimum cuts. Okay. And since near minimum cuts have expectation very close to 2, it might seem intuitive that this property just follows from the fact that we sample a tree which respects the marginals of the LP. However, this is actually not the case. Not every tree distribution respecting the marginals has this property. So for example, say our LP solution is a complete graph on n vertices with 2/n on every edge. Then the near minimum cuts are just the degree cuts. And a valid marginal preserving distribution is to write this point as a convex combination of n stars. But now in every tree we sample, every near minimum cut is odd. So this distribution fails spectacularly even though we're respecting the marginals. And to be clear, the issue here is that even though the expectation of each near minimum cut is 2, our distribution doesn't concentrate at all. The degree is 1 or n minus 1. So this property is at least kind of non-trivial. To get a handle on this, I'll introduce some key properties of our tree distribution, and I'll also discuss the class of so-called Strongly Rayleigh distributions. Okay, so thankfully, lambda uniform spanning trees have this property, as do most trees we sort of find in the real world. So to help obtain this property, we first noticed that lambda uniform distributions are part of the class of what's called Strongly Rayleigh distributions. So let me define SR strongly Rayleigh distributions quickly. Consider a distribution mu over subsets of a set M, and for us, these will be trees over the edges of a graph. Then let mu of S be the probability that we select a set S. Then the distribution is strongly Rayleigh if its generating polynomial P of mu is real stable. So what is this P of mu? If you assign each element I of the set M a variable zi, then the generating polynomial is this object. You sum over all sets in the support, and you multiply mu of S times the product of the zi's for each element I in the set. And we call a polynomial real stable if it has no zeros in the upper half of the complex point. If this is the first time you're seeing this, this is likely a bit confusing, but to give a concrete example, z1 plus z2 is real stable, but z1 times z2 plus 1 is not. Because if we set z1 equals z2 equals I, then this polynomial is 0, and the roots all have, and the variables all have positive imaginary values. So it's in the upper half of the complex point. SR distributions have strong closure properties. So for example, projection, meaning we can select any subset of elements and the distribution restricted to that set is strongly Rayleigh. And conditioning, after conditioning on an element being in or out of the sampled set, the resulting distribution is still SR. And it also satisfies negative dependence and negative association, and therefore has useful concentration properties that we were missing. Any questions? So one of my favorite SR properties is basically a strong form of concentration. And I'll put it in terms of our spanning tree distribution for clarity, but it holds in general. So here's the claim. For any cut S, there exists some number of Bernoullis such that the law of the size of the intersection of this cut with the tree is equal to the law of the sum of these Bernoullis. In other words, for any K, the probability the size of the intersection with the tree is K is exactly given by the probability these Bernoullis sum to K. And this gives us a pretty nice constant. It says that any near minimum cut is even with probability at least 0.43. And note this is stronger than just saying many near minimum cuts are even. It's saying every near minimum cut has a probability of being even. So this is a nice property. And in a sense, this tells us that lambda uniform spanning tree distributions sampled from the TSP-LP are locally Hamiltonian. In other words, many vertices should have degree 2. And in fact, in general, adjacent vertices should have a chance to both have degree 2 and so on. So given this, first let's try the following natural idea. Set an edge's slack to be minimal if it's in no odd near minimum cuts, and otherwise set it to 0. This is obviously feasible, but can it generate enough gain? This strategy actually works in a simple case when the only near minimum cuts of the graph are the degree cuts. And in this case, we can use a lemma which is proved in the paper from Oveskar and Sabarian Singh in 2010, that any two near minimum cuts are even simultaneously with probability at least some constant p. And there's one important exception here, hence the star, but I'm not going to go into that in this talk. So given this, the degree cut case is easy. Pick an edge E. It's only in 2 near minimum cuts. It's endpoints. Then with probability p, the tree that's selected has even intersection with both of the endpoints. In other words, with probability at least p, any edge E is in no odd minimum cuts. And just using the strategy from the previous slide, each slack now has negative expectation. It's 0 if an endpoint is odd, and negative eta over 4 times xe otherwise. However, unfortunately, this strategy cannot work in general. In some sense, this is the strategy used by the 2010 paper to show that their algorithm beat 3/2 for graphic CSP, as it's possible to show that some edges have this property, that there are no odd and near minimum cuts. But this approach is sort of fundamentally doomed for the general case, as some edges may be in many, many near minimum cuts, and these edges may actually be the expensive ones. However, hope is not lost. Maybe if we can obtain a laminar family of near minimum cuts, where at each level we just have degree cuts, we can apply this logic at every level, and somehow, through some inductive approach, deal with edges that appear at many levels. And this is exactly what we do. So the rest of the talk now naturally divides into two pieces. First, I'll show you how to obtain a laminar hierarchy. And in this section, I won't use any properties of SR distributions or lambda uniform trees. And in that sense, you can think of it as actually a reduction to the hierarchy case that's valid for any algorithm which samples a spanning tree that respects the marginals of the TSP-LP and then adds a matching. And given this hierarchy, in the second part of the talk, we will exploit properties of SR distributions and lambda uniform spanning trees to construct a Slack vector that works on any laminar family of cuts. Okay, so now I'll tell you the gist of this reduction.
Nathan, quick question. In this sort of two-part breakdown, where do you lose the sort of constants the most, or you lose in both?
The second step, I would say. I mean, the first sort of does limit to some extent how good your constant can be, but then this one really, really blows it up. So, yeah. Okay, so to obtain a simpler structure of near minimum cuts, we're going to consider actually a different solution to the Held-Karp linear programming. We're going to consider the average of opt and the obtained point x. So this point z is clearly in the TSP polytope. It's the convex combination of two feasible points. And actually, it costs the most opt. And note that we don't actually need to know opt for our algorithm, since we're just showing the existence of a cheap solution to this matching LP. So this appearance of opt is only in the analysis. Okay, so why do we do this? It turns out that the point z has a nice near minimum cut structure. Every cut less than 3 is now an interval of the optimal cycle. So suppose you take a cut that's not an interval, then you get at least 4 opt edges, each having fractional value 1/2 in z. And we also get half of x. So this says that any cut not along the optimal cycle has z of delta of s at least 3. So this green cut, we definitely don't have to worry about. This red cut, we may have to worry about, but actually only if it's also a near minimum cut of x. Okay, so recall we're trying to show that there's a good solution to the matching LP, and previously we used half of the optimal TSP-LP solution as our initial point. Now we're going to instead start with half of z. So now we'll set ye to be ze over 2 and then add our Slack vector. And now we only need to worry about cuts that are intervals of the optimal cycle. So this is a possible set of near minimum cuts of z. And the expected cost of this matching is again at most opt over 2 plus the expected value of our Slack, which will be negative. And notice that sort of at this point, we lose the ability to prove anything about the integrality gap. But so be it. So this is great. Already this simplifies the structure of near minimum cuts. So now in this picture, there are 2 things going on. You have cuts that are crossed, like these green cuts, and cuts that are nested and sort of already form a laminar family, like these red cuts. And all that now remains is to handle these green cuts. And to do this, we need 2 simple tools. The first tool is one we use over and over again in our result, not just in this section. And the property is as follows. Let S be a set, which is a near minimum cut with respect to X. Then with high probability, the sample tree T restricted to S is itself a tree. So formally, the probability that t intersect the edges of S is exactly the size of S minus 1 is at least 1 minus eta. So as in the picture on the right, this means the set inside of S induces a tree. And note that I'm talking about X here, not Z, because X is the distribution that we actually sample our tree from. We didn't know opt in our algorithm. So all probabilistic statements will be with respect to X. Okay, so here's the proof, and it's true of any tree distribution with respect to marginals. So what's the expected intersection of T with the edges of S? It's half of this degree sum, which is 2 times the number of vertices in the cut, since every vertex has degree 2, minus the edges leaving the cut, and divided by 2. And this is at least the size of S minus 1 minus eta by our assumption on the size of the cut. However, we're sampling a tree, so we can never exceed the size of S minus 1 edges inside the set. So, otherwise we would get a cycle. So just using expectation, the probability we get exactly S minus 1 edges is at least 1 minus eta. And our second tool is a basic fact about crossing cuts. If S1 and S2 cross, meaning one is not a subset of the other and they're not disjoint, and each are 2 plus eta near minimum cuts, then their intersection, set difference, and union are all 2 plus 4 eta near minimum cuts. So in particular, the red, purple, and blue sets here are 2 plus 4 eta near minimum cuts. And now I claim that with high probability, there's exactly one edge from red to purple and exactly one edge from purple to blue. So kind of along this optimal cycle. So why is this the case? First, we're going to condition on red, purple, blue, S1, and S2 to all induce trees. From the previous slide, this happens with very high probability, at least 1 minus 16 eta, just using a union bound. But now, look at red and purple. They each induce a tree. And S1 induces a tree as well. So they must share exactly one edge. This is because they share at least one edge. They're connected. They're in the same tree. But if they shared 2 or more edges, there would be a cycle. And similarly from purple to blue. So we get something that looks exactly like this. And in a sense, I can't get too specific, but this should tell you that when we have crossing cuts, the tree, at least to some extent, mirrors the optimal cycle. This is a kind of stronger form of the locally Hamiltonian property that only arises when we have these types of cut structures. And to make a long story short, we can use these ideas to reduce the problem to a laminar family of near minimum cuts. And again, we see this as a kind of reduction since it's valid for any distribution of spanning trees that respects the marginals of the TSPLP. So now we'll move on to the next section, constructing our slack vector. Are there any questions about this section? All right. So now we can forget about the optimal solution. And here's a valid hierarchy we might obtain. This little blue person is happy now, where I'm dropping the optimal cycle to emphasize that we're looking at the edges of X now. But feel free to imagine that the hierarchy is superimposed on the optimal cycle. So here each color represents edges at different levels of the hierarchy. And an edge's height is just defined by the level of the hierarchy that contains both of its endpoints. So here the pink edges are higher than the red and the blue edges, and the purple edges are again higher than the pink edges. And at a high level, what we'll do now is as follows. We initialize all slack at 0, and then we define local conditions for decreasing slack. We will decrease an edge's slack when it is in no odd cuts on its top level. And this matches the intuition that we perform induction over the degree cut case. So for example, the top level of these pink edges is this pink cut. And now we view this pink cut in isolation as a graph with only degree cuts. viewing these two green sets as just contracted points. And for the pink edges, these green cuts are called their top two cuts, and this is terminology I'm going to use in this section. And now the pink edge's local condition is the same as in the degree cut case. We're going to reduce their slack when both of the green cuts are even. Unfortunately, this reduction may cause issues lower down in the hierarchy, and basically arguing about this type of event and how to fix it is the essence of our inductive approach. So more formally, we decrease slack for this local reason if an edge's top two cuts in the hierarchy are even. So for example, look at our pink edge E. L2 and R2 are its top two cuts in the hierarchy. If the black edges here represent our sampled tree, here we would not reduce SE. They're both odd. This is intersection 3, this is intersection 1. However, if we sampled this tree instead, both cuts are even, and now we can reduce SE by its maximal possible reduction. However, we only condition on L2 and R2 being even. We only look sort of very locally around us. And we don't know whether L1 and R1 are even or not. And if they're odd, these constraints are actually violated now in the matching LP, since they're very nearly tight to begin with. So we'll actually increase the slack of other edges to make up for this decrease. In this case, R1 is odd. So we must increase some edge Fi to make up for E's reduction. L1 is even, so no increase is needed. And what we'll end up doing is performing a matching such that when E is decreased and a cut lower in the hierarchy is odd, an edge group of similar fraction will increase. That's matched to E on this level. So here, say F3 is matched to E on this level, and they should have roughly the same fractional value. Then whenever E decreases its slack and R1 is odd, F3 will increase its slack by the same amount. And something important to keep in mind here is that if an edge is reduced, it definitely does not have to increase its slack for any edge it's matched to. This is because it only has to potentially increase slack for its top two cuts, but the decrease event implies both of these cuts are even. So the increase and the decrease events are disjoint, and it only remains to show that the expected decrease of an edge is greater than its expected increase. Okay, so now I'll formalize our approach even a bit more. So first, for every set S in the hierarchy, we will find a fractional matching from the edges inside of S to the edges in the cut, the edges going higher, such that no edge is matched to more than its fraction. So for example, this purple edge E is matched to 1/2 of the value of the orange edge F. And in this way, we have a kind of one-to-one matching from edges that stay at level I to edges that go above level I. And given this, we can show that the expected slack of an edge is negative in the following way. So first, we start with all slack at 0. Then we decrease SE by XE times eta over 4 if its top two cuts induce trees and are even. And we'll do this with probability exactly P, where P is the lower bound on the probability of this event across all edges. And basically, this P is a kind of normalization. We decrease all edges with the same probability to ensure that the amount an edge needs to increase for its matched edge does not exceed the amount it decreases. So step 2 may now violate some constraints in the matching LP for cuts that are odd and lower in the hierarchy. So in step 3, we increase edges to compensate for decreases made on the edges that they're matched to. And now we can compute the expectation of S of E. And suppose it's only matched to one edge, F for simplicity, as in this case. Then the expectation is this reduction event, negative P times eta over 4 times X of E, plus the expected increase. Which is P times eta over 4 times XE times the probability that S prime, the cut it shares with F, is odd given that f is decreased. So it should be clear that as long as this probability is bounded below 1, we're sort of done, at least, assuming that what I've told you is true. Okay. And so notice that we require an edge's top 2 cuts to induce trees in order to reduce its slack. It turns out that this implies a useful independence property that we can use to bound this probability below 1. So first recall that every near minimum cut is a tree with very high probability, so requiring this is not difficult. And it turns out that if this event occurs, then the distribution decouples into 2 distributions, one lambda uniform distribution inside S and one outside, where the one outside treats S as a contracted vertex. And furthermore, the marginals change by most eta when we condition on a near minimum cut to be a tree. And this should be kind of intuitive since it occurs with such high probability. So to say pictorially what's going on, suppose I have a set S and I condition on the event that S induces a tree. Then our spanning tree distribution decouples, and we can model it as first picking a tree inside of S, so on these red edges, then contracting S, and independently choosing a tree on the remaining edges. So this is what tree conditioning does. It decouples our distribution. So consider this red edge now, and suppose that we've reduced its slack. Then its top 2 cuts, marked in red, are even, and they induce trees. So now the distribution decouples into 2 independent ones, one on the blue edges and one on the red edges. And now it's not so difficult to imagine that any vertex in the blue set has a constant probability of being even regardless of the behavior of the tree sampled in this red set. So consider this green cut and say the edges in the blue set have expectation 1.1 or really anything bounded away from 1 and 2. And note that the expectation must be actually between 1 and 2, ignoring eta factors. So this is not such a strict requirement, actually. Then using SR properties, there's an independent and constant probability that the blue edges have intersection 1 with the tree, and an independent and constant probability that the blue edges have intersection 2 with the tree. And when I say independent, I mean independent of the red edges. Therefore, this blue independent tree has some chance to fix the parity of the green cut, regardless of the parity of this red edge. So whatever happens in red, with some probability, blue fixes it. So essentially, due to this tree conditioning, condition on the event that an edge is reduced, there's always a constant probability that any cut lower in the hierarchy is even. And there are, of course, some caveats here. For example, I haven't said what happens if this intersection is very close to 1 or very close to 2, but hopefully this gives some intuition as to why we can obtain this. And this would give the desired expectation for any S of E. So it remains to talk about the matching. And it turns out that if S has at least 3 near minimum cuts inside, it's not hard to show such a matching exists up to some eta error, which we never care about. Sorry, eta. However, if the size of S is 2, this is really not possible. And this is just because x of E of S is approximately 1, and delta of S is 2. So yeah, this matching will fail. And I'll call edges whose top cut has size 2 bottom edges. Yeah, and these edge types must be matched to actually twice their fraction. And it turns out that every bottom edge's top cut looks exactly like this. It's 2 near minimum cuts that share fraction approximately 1. So this is exactly the setting we're now concerned with. And to handle this case, we proved 2 probabilistic lemmas about SR distributions, which are possibly of independent interest. We first proved that for any k disjoint sets, each with expectation close to 1, there's a constant probability that each set has intersection exactly 1 with the tree. So in this example, there's a constant probability each color has exactly 1 edge in the tree. More formally, we prove a generalization of a lemma from a paper by Gervitz from 2006, we show that if you have k disjoint subsets of the edges, say, and their expectation is close to the all ones vector, then the probability every set has intersection 1 with the tree is a function of only k and epsilon, so independent of m or n. And I'm using t here for tree, but again, this holds for general SR distributions. And I call this a generalization as this was previously known for k disjoint subsets that each had expectation exactly 1, but now we allow some deviation. And actually, recently, Gurvitz proved a related theorem, which has a much better dependence on k, but is slightly more restrictive due to this square root of k here. So why is this interesting? The main use of this tool is to strengthen the conditions for decreasing an edge, and therefore reduce the fraction that we need to match bottom edges to. So consider the blue edge E of value epsilon, where both the left and the right bottom edges are matched to it. So suppose SL and SR are E's top two cuts. Then this lemma tells us that there's an event with constant probability where E is even in its top two cuts, SL and SR, and all 4 of these blue cuts are even. So this would mean that the bottom edges do not actually have to be matched to these edges at all. So why is this true? First condition on the event that E is not in the tree. This event occurs with probability at least 1 minus epsilon. And the distribution remains SR by our closure properties. And furthermore, by negative dependence, the expectation of the remaining edges changes by at most epsilon. So now consider the sets A, B, C, and D. Then this probabilistic tool says that since their expectations are all very close to 1, in fact, we're actually essentially 2 epsilon away from the all ones vector. It says that there's a constant probability that every set has intersection 1 with the tree. And furthermore, it's easy to condition these bottom edges to have intersection 1 with the tree. So now all 6 cuts are even if this occurs. And actually, this is the one time epsilon will not be that small. This works for all epsilon bounded below 1/2. So this is pretty powerful. And second, we prove a related fact for 2 disjoint sets A and B of expectation again close to 1. We showed that there's an event of constant measure which approximately preserves the marginals of all edges in A and B. And we'll give you that A has intersection 1 with the tree and B has intersection 1 with the tree. So in this example, such an event exists which will preserve the marginals of this edge E and make sure it's conditioned on this event. It's in the tree with probability approximately 1/2. And here it is written formally, but it just matches what I said. For any 2 sets A and B with expectation close to 1, there's a marginal preserving event, EAB, of constant measure, in which each of A and B have intersection 1 with the tree.
So the difference is that here it's marginal preserving, whereas previously, in the previous lemma, it wasn't.
Exactly. So if you don't use this lemma, then it could be that when you condition on A to be 1 and B to be 1, certain edges have very high probability and certain edges have very low probability. So it may skew the distribution quite a bit.
Okay.
And using this, we can now change the rule for reducing bottom edges. Instead, we're going to use the tool I just mentioned. We're going to reduce a bottom edge with disjoint sets A and B going higher from its left and right top sets, only when this event EAB happens and when this bottom edge has intersection 1 with the tree. So then whenever E is reduced, both blue cuts are even and marginals are preserved. And as you can see, sort of from the structure of these inductive arguments, we're going to need to talk about the probability that another cut lower in the hierarchy is even conditioned on a bottom edge being reduced. But if we know that marginals are preserved, at least approximately, this allows us to say much stronger things about this. And it gives us a huge amount of control over the probability that a cut lower in the hierarchy is even conditioned on a bottom edge being reduced. So that's all I can really say about that. And basically with these ideas and some elbow grease, we get a small improvement over Pistophitis. So as for next steps, first, because of Z, as I said, we don't get the integrality gap. And it would be nice to prove this, and we think it might be doable. The use of opt is, we expect, not sort of fundamental to the proof, although it does make the cut structure simpler. Or conversely, is there a proof which only uses opt edges, i.e. define slack on opt instead of on X? I think if such a proof existed, it might be significantly simpler. And secondly, I swept a lot of things under the rug. One big headache is the existence of edges whose top two cuts are not even simultaneously with constant probability. In particular, these are edges whose top two sets share fraction of exactly 1/2, or very close to 1/2. We're able to show that these edges cannot appear too often, but we'd like to remove them entirely. So we ask, are there techniques for handling these edge types? And actually getting rid of these edges would go a long way towards simplifying our proof and would improve the constant by many, many orders of magnitude. So this would be very nice. And in general, stronger theorems concerning SR distributions will definitely help. But maybe most importantly, are there totally new ideas for analyzing this algorithm? We know no instance where it does worse than 4/3. So either there's a bad instance lurking out there, or we need a very different approach to the analysis. So with that, thanks so much for listening. Here's a picture of some TSP soup by Bosch. Yeah, actually, please let me know if you're interested in talking about any part of this result offline. The paper is long, and so it may look a bit intimidating, but a lot of the apparent complexity arises from dealing with these special cases, like these 1/2 edges I mentioned. So I'd be happy to help cut through any confusion. And of course, I'd love to talk about any ideas for improving or simplifying things. Just shoot me an email. So thanks, I'd be happy to take any questions.
Thanks, Nathan. I guess I'll clap for all of us. So if people have questions, maybe they can unmute themselves. If there's too much contention, then I can try to resolve them. But I see maybe there was a question. So I have a question, which is, do ideas in your new paper help somehow simplify or improve the half integral case that you guys had proven last year?
Yeah, that's an interesting question. I think not exactly, but some ideas that were generated along the way definitely could. So that's, yeah, something we thought about a little bit. And there should be definitely a better proof and maybe a better constant for the half integral case now. We'll see.
Yeah.
But yeah, I think sort of part of the idea was getting this laminar hierarchy. And in the half integral case, you're looking at only minimum cuts.
Mm-hmm.
So you don't really need to do that. So that was one aspect that, yeah. But it could be that this sort of generalized Gurvitz lemma also has some ways to simplify it. If not, you know, it wouldn't make the constant better because that lemma has like some double exponential dependence and stuff, but it could make the proof simpler, yeah.
Other questions? Maybe I'll keep asking. Yarek has a question.
I have a general question. What's your feeling? Which point was the crucial part? That once you had the idea, then you knew it would work. Like, what was the cornerstone here?
I mean, I really think there were two. Like, the first was getting this hierarchy to happen. And you can go about this, you know, in several routes. One is looking really in detail at the structure of these near minimum cuts and looking at these so-called polygon representations and so on. And it seems like there should be something there. But once you start using opt, it becomes a lot easier to sort of do this reduction and get through that. So it's not clear that, you know, without opt you would fail. In fact, we probably think you could make it through, but it really made it a lot easier. And then in the hierarchy, you know, that was a lot of, yeah, I think this lemma about conditioning and preserving marginals was really very helpful there. And the Gervitz lemma like gave us a lot of intuition sort of about what events should be true. So, you know, instead of like rigorously checking like, oh, does this event have constant probability? You could just check the Gervitz lemma. So yeah, I guess sort of these three different pieces were all sort of crucial in their own ways.
Thanks.
Yeah.
Maybe I'll ask a question, Nathan. Thanks for a great talk. The reason you only look at top two sets is because even though you have a hierarchy where you have more than two children, there are only two that are relevant for each edge. Is that why?
Yeah, that's roughly the case, but in some cases we actually look a little farther down, and this is exactly what's going on in this slide here. So here, this edge E is looking at the top two sets, SL and SR, but now it's like, okay, I'm also going to look down one more level and make these blue cuts happy. So the use of this tool is actually to strengthen it and not just look at the top two cuts and look at, say, the top 6 cuts or something. We never go beyond really like 6. That would you could, but might be more complicated. But yeah, that's a good question.
So do you think there is something to be had and it just requires a certain steel to just sit down and try to do it? Or are the improvements so small that perhaps we should be looking in other directions?
Yeah. So the thing is, these edges that are very close to 1/2,
Okay.
with no probability of being even, you have to do something sort of very weird currently. You have to like look at edges that are, you know, a little bit bounded away from 1/2 and say, oh, we can do nice things here. And, you know, you're looking at edges that are very close. So then the probability they're even in their top 2 cuts is again very small. So that's sort of one big issue. I think if someone came along and said, oh, if you just look at a slightly different distribution, or you like somehow perturb the polytope a little bit to get rid of these 1/2 edges, then the proof would be a lot simpler. I don't think you would get for like 4/3 or even 1.4 or anything. I think that requires like really new ideas, but I think at least you could get, you know, maybe something like the 1.4999 from half integral, and you could get a much more pleasing proof. So I think that's one big thing. But yeah, I mean, part of this talk, maybe you should come away and say, okay, that's cool, and maybe this algorithm is good, but maybe we should try a different analysis too. So yeah, I don't know.
Other questions? Ravi?
It was just a clap.
Oh, okay. So maybe we can have Nathan around for a couple more minutes in case people want to ask him questions informally. Let's thank him again for a great result and a great talk. And I guess we'll start again in about 20 minutes for the next session, so people can take a little coffee break.
Thanks a lot. An impressive result and a great talk.
So actually, now that I've made this thing informal, I might as well ask you one last question. So since everything's kind of breaking down near the half point, does this give any sense that is the half integral case actually the hard case? I mean, what's...
Yeah, I mean, there's definitely that definitely has crossed our mind that, you know, maybe there's a reductions to half integral case or something like this, because the half edges are so hard. That's weird. I don't know, like, yeah, I mean, obviously there's some probabilistic reasons that half edges are hard, but beyond that, it's like, it's not clear to me why they're so difficult.
Cool.
So if the half edges have little weight then your guarantee would be much better.
Yeah, then you're also happy, yeah. And actually what we do in the end is we say, okay, first sort of solve things on the edges that are not 1/2, you gain a little bit, and if this solution has any weight, you're done. Otherwise, you sort of increase the slack on just those edges, and then on the half edges, you can decrease because you've done this everywhere else. So we actually have to do this 2-step process because of half edges. So if they weren't there in the first place, we could just do the first part and remove a lot of this analysis, yeah. Or if they had little weight.
So I'm going to sign off. Thanks again, Nathan, and I'll see you guys in like 5-10 minutes when the next session starts.
Thanks.
Okay, unless there are any last questions, I'll sign off as well. Thanks, everyone.